So this is this section called Linear Kinematics 2. Again, kinematics is the study of motion. Linear just means in a straight line. We're not doing fancy curvy stuff. It turns out that if you can understand straight line motion, it's not too much more complicated to do the stuff that looks a lot more complicated. We won't do much of that, but we'll do some mostly straight line stuff just to understand the basics. So in this section, we'll talk about position, time, and velocity like we already have, and then we'll introduce acceleration. Again, I think you're probably familiar with most of these terms, but we're sort of putting concrete definitions to them. So let's just go through a glossary for a second of what these terms are, right? We've introduced a whole bunch of them as we've discussed. So T1 is the time for the start of observation. Often we just make that 0. It's like if you were watching some experiment and you started your stopwatch when it began, T1 would be 0, right? Usually that's what we have. And if a question doesn't give you a beginning time, we just assume it's 0. And then T2, which is the time at the end of observation, just represents the total time this event occurred. So delta T is the change in time, is T2 minus T1. If T1 is 0, it's just T2, and sometimes we'll even just call that T. T1 is 0, we'll just call T2 T. But anyway, delta T is just the time, the elapsed time of observation. Right? X1 is the starting point, X2 is the ending point. So X1 is the position of the object at the starting time, X2 is at the ending time. Delta X is the distance traveled. Sometimes we use D for that. V1 is the velocity of the object at the starting time. V2 is the velocity of the object at the ending time. V average is the average velocity. It's the change in position divided by the change in time. Notice that's different from V1 or V2. The object could have different speeds at the beginning and at the end, and its average speed is just how far it went divided by how long it took. And so it could be speeding up or slowing down. We didn't really talk about that in the last section, but it sure can. Our velocities last time were constant pretty much. It turns out you can also say the average velocity is the initial velocity plus the final velocity divided by 2. So for example, if I started at 0 meters per second, and I sped up to 20 meters per second, then my average velocity would be 0 plus 20 divided by 2, or 10 meters per second. Hopefully that makes sense. This definition of the average is sort of, I think, what we're all familiar with, right, from test scores. If you had a test that you made an 80 on and a test you made 100 on, the average score you had would be 80 plus 100 divided by 2, or 90. And finally, A is what we call the acceleration. And we're going to talk about the acceleration in this section. Let me just say one more thing about that. It would be good for you to just sort of memorize what those terms mean. You don't have to, but it would be helpful probably when you're answering questions on a test. X1 is the starting position. X's are positions, V's are velocity or speeds, T's are times, A's are accelerations. The 1s and 2s should be sort of self-explanatory. So let's say the velocity of a car relative to some coordinate system is V1 at time T1. So maybe my car enters an on-ramp at 20 miles per hour. Right? Later at time T2, the velocity is V2. Now my car enters the on-ramp at 20. When it gets off the on-ramp onto the interstate, it's doing 60, say, or something while it's speeding up. So the change in velocity then would be 60 minus 20, or 40, right? The acceleration is defined as the change in velocity divided by the change in time. So 40 meters per second divided by how long it took to do that gives me the acceleration. And so let me just do an example of this, right? If I said my V1 is 20, I'll say miles, let's say 20 meters per second, just to keep things in SI units, meters per second, and V2 is equal to, I don't know, I'll just make up a number, 40 meters per second, right? And I can say this was at T1 equal, we'll just pick 0 for that. This is when my car enters the on-ramp. And it takes, how long does it take your car to go through an on-ramp? I don't know, say T2 is is 5 seconds, right? What we're saying is the acceleration is the change in the velocity divided by the change in time. It's the rate at which your speed is changing. That's how it's defined. Hopefully that matches your intuition for what an acceleration is. When you step on the gas, the greater your acceleration is, the greater you're speeding up. And so this is v2 minus v1, because that's what delta v is, over t2 minus t1. In this case, that's 40 meters per second minus 20 meters per second over 5 seconds minus 0 seconds, and that's equal to 20 meters per second, because 40 minus 20 is 20, over 5 seconds, and that's 4, because 20 divided by 5 is 4, and it's meters per second, right? That's what that is. And these units should sort of make sense to you, right? It's 4 meters per second every second. So if you were going at 20 meters per second, after 1 second, you've increased your speed by 4 meters per second, because you're increasing it by 4 meters per second every second. So after 1 second, you'd be going 24 meters per second. After 2 seconds, you'd be going 28. And then after 3 seconds, 32. And then after 4 seconds, 36. And then at 5 seconds, you'd be doing 40 meters per second. You can combine these two this way and say this is 4 meters per second squared, right? It's kind of like saying 1/2 divided by 2. A half divided by 2 is a quarter. It's equal to 1 over 2 times 2, which is 1 over 4. How the math works on that. And so this, once again, is the units we had, the SI unit for acceleration, right? And that's what we should get, because that's what we're evaluating. Let me switch back. So acceleration is defined as the change in velocity divided by the change in time. We have it here. Notice that just as in a position versus time graph, the slope was the velocity. Now in a velocity versus time graph, the slope is the acceleration. And so if here's just an example. Suppose a car is traveling at 4 meters per second. It equals 2 seconds, and then accelerates to 10 meters per second at 5 seconds. This is very similar to the calculation we just did. It's 10 meters per second minus 4 meters per second, because that's the final velocity minus the initial, over the final time minus the initial time. And once again, we get 2 meters per second squared as a result. We can also calculate the average velocity of the car, right? The average velocity was the initial velocity, which was 4 meters per second, plus the final velocity, which was 10 meters per second, divided by 2, which is 7 meters per second. It's 14 meters per second divided by 2, which is 7 meters per second. We can use this information now, the average velocity, to go back to the previous section and calculate how far it traveled, right? If we know the average velocity of the car is 7 meters per second, and this is what the average velocity is, then we know that the change in position, if we multiply both sides of this expression by the change in time, we get the change in position is the average velocity times the change in time, or it's 7 meters per second times 3 seconds, or 21 meters. Right. So that's a little bit of math there. Let me go back and do the one we had on the board here. So once again, in this version, I'm going to do the exact same thing I did there a second ago. I can say, look, V average, the average velocity for this car, is V1 plus V2 divided by 2. Right? And so that's 20 meters per second plus 40 meters per second divided by 2. 20 plus 40 is 60, divided by 2 is 30. Hopefully, if somebody just asked you this without knowing any physics and say, hey, look, the car started at 20 meters per second and it finished at 40 meters per second. How fast was its average speed? You would say 30, right? It's halfway between those. That's what this formula gives you, right? And now we can go to our original definition of the average velocity. Again, the average velocity can be written two ways. V average is the change in position divided by the change in time. That's how we defined it. And then what I said on the slide we just looked at is I said, look, we can solve this for the change in position. I didn't say anything about how long the on-ramp was in this discussion. I said at the beginning of the on-ramp it was going at this speed, at the end of the on-ramp it was going at this speed, That's how long it took, right? And so we can rearrange this equation by, if you remember a little bit of your algebra, multiplying both sides of this equation by delta t, right? And then these two guys cancel, and I get delta x is equal to v average times delta t. And that's 30 meters per second times 5 seconds, right? That's what my delta t is. T2 minus T1 is 5 seconds. And so that's 100, if I have a little room here, 150 meters. Did I get that on the screen? I think I did, right? And so the change in position for the car, the length of the on-ramp is 150 meters. Okay. So let's do another one. This is saying, what's the acceleration of a car that is traveling at 40 meters per second and comes to a stop in 5 seconds? So there's a lot of information in this problem, or there's at least some information in this problem that wasn't said. First of all, you should look at this problem and say, well, that 40 meters per second, what is that? That's its v1, right? It doesn't say anything about what its velocity is, but you know that they're talking about a velocity here because this is in meters per second, and that's a velocity. So a car is traveling at 40 meters per second, right? I would call that v1. And then it comes to a stop. So after 5 seconds, it has stopped. And so that means that its final velocity is what? It's 0, right? So let's just work this out on the board here. Here we go. We could say, look, in this problem, v1 is 40 meters per second, right? And v2 is equal to 0 because it stopped. And it just, all it really tells us is that delta t is 5 seconds, right? That's how long it took for that to happen. And so if I wanted to, I could say, well, t2 is 5 seconds and t1 is 0. But I won't even need to really do that because it's asking me what the acceleration is, and the acceleration is the change in velocity divided by the change in time, right? And I have to be a little careful when I do this because if you remember, the change in velocity is v2 minus v1. And v2 is 0, so it's 0 meters per second minus 5 meters per second over, sorry, not 5, 40. Divided by delta t, which is just 5 seconds, right? And so the acceleration is minus 8 meters per second squared. The minus sign comes from here, and what this is saying is that it's accelerating in the opposite direction of the velocity. And so, in other words, in the previous problem, we were adding 4 meters per second. That's what the acceleration was doing. Now we're subtracting 8 meters per second every second. So after 1 second, it's going 32, and then 24, and then 16, and then 8, and then 0 meters per second. That's what the acceleration is telling it to do. Also in this problem, just as in the previous one, we can calculate the average velocity, right? The average velocity is v1 plus v2 divided by 2, and that's 0 plus, got them backwards. That's 40 meters per second plus 0 meters per second divided by 2, which is 20 meters per second. Again, to me, that's a common sense one. If its initial velocity is 40, its final velocity is 0, its average was 20, right? And I can use the same formula I used before. V average is the change in position divided by the change in time, and that's equal to, that means that the change in position, if I multiply both sides by delta t, is the average velocity times the change in time, and that's 20 meters per second times 5 seconds, which is 100 meters. So that's the stopping distance of the car. So now let's talk a little bit about the graphs, right? This is going to look like exactly the same argument I made for the slope in a position versus time graph being the velocity. Notice in this graph, this is not a position versus time graph, this is a velocity versus time graph, right? And so when I draw a line here, my change in the vertical axis is change in velocity, my change in the horizontal axis is change in time. Since the slope is the ratio of those, right, in a position versus time graph, the acceleration is the slope. I'm sorry, in a velocity versus time graph, the acceleration is the slope. So what we would say about this graph, if I asked you, tell me something that's true about the object that's creating this line, right? You could say, well, one, the acceleration is positive because it's tipped upward. And you could also say the acceleration is constant because the line is straight and not curvy. Right? So those would be two things you could say about the vehicle that's true, or the object. Recall that the acceleration is a slope in a velocity versus time graph. Since the line is straight and not curved, the slope is the same everywhere. This means the acceleration of the car is constant. Note that the speed is steadily increasing, so the velocity is not constant. You guys see that hopefully, right? As time is marching forward here, the velocity is increasing, right? The velocity at any point, like if I pick this point here, the velocity is whatever I get when I go straight across to this axis, right? And so the velocity, this is a car that's steadily speeding up in its velocity. Unlike in the position versus time graphs, right, a straight slope, those were traveling at a constant velocity because the slope was constant in those. Here the slope is constant, and that means the acceleration is constant, not the velocity. So now we can say, we can look at a similar graph. These graphs I'm going to show you are going to look a lot like the last ones, except they're not for a position versus time graph. They're for a velocity versus time graph. And so just as before, the steeper line means a steeper slope. And in this graph, that means a greater acceleration. This car's speed is changing the fastest. This car's speed is changing a little less fast. This car's speed is changing less fast still. But all three of these cars are speeding up. Their acceleration is constant for each of them. They're all different, but they're constants, right? And they're positive. A is accelerating the fastest, B next, and C next, and so on. So recall that in a velocity versus time graph, the acceleration of the slope, since A has the steepest slope, it has the greatest acceleration. Since car C has the smallest slope, it's got the smallest acceleration. Oops. What's the acceleration of this car? So if you remember that the acceleration is the slope, since delta V is 0 in this, right? There's no change in the velocity. The acceleration has to be 0, right? The velocity at this point, to get the velocity at any point, you just go straight over to the vertical axis, and that's wherever it meets the vertical axis. But every point on here, right, it's along the same horizontal line, so it meets the axis at the same point, and so the speed is constant here. And that means, for this case, the acceleration is 0. Notice it doesn't mean the velocity is 0. The velocity is whatever value is on the axis at this point. It's a positive number because it's above the origin, right? But it's the same all the way across. So this is just a car traveling at constant velocity. Maybe this is the graph of a car on the interstate in cruise control. Something like that. Whereas these previous graphs, these would be cars on on-ramps maybe. This would be a sports car on an on-ramp, and C might be a semi-tractor trailer on an on-ramp. Or my car on an on-ramp. I have a pretty weak acceleration in my car. So this is just a mathematical version of what I just said. Since V2 and V1 are the same, delta V is 0. This should say since the velocity V of the car never changes. I'll have to fix that typo. That's the velocity of the v. The position changes because the velocity is not 0. So now what is this car doing? Hopefully you can see this car is slowing down. Its velocity is greater at v1 than it is at v2, and so it's got a negative acceleration. It's got a positive velocity and a negative acceleration, and so it's slowing down. All right. So let's look at this graph. It's a little, this is a t here on the bottom axis. So now I'm back to a position versus time graph. This is a tricky question, so look at this carefully. The acceleration, so in a position versus time graph, the slope is the velocity, right? This is what we talked about in Kinematics 1. All of these lines are straight, right? And so in a velocity versus time graph, the slope is in a velocity versus time graph, the slope is the acceleration, but in a position versus time graph, as we have here, the slope is the velocity. All of these curves are straight lines, and so they represent constant velocity. And so in every one of these cases, the acceleration is 0. So remember, in a velocity versus time graph, the acceleration is the slope, but in a position versus time graph, the acceleration is the velocity. And since all of these lines are straight, the velocity is the same all the way along them. This line A, the slope is the same everywhere, so its velocity is the same everywhere, and so its acceleration is 0. If the velocity is constant, the acceleration is 0. So all three of these curves represent objects that have 0 acceleration.